Hello everyone, and welcome back to the C-Squared channel. Our Milky Way galaxy contains about 250 billion stars of various sizes, ranging from the Earth-sized white dwarf stars to the enormous hypergiant stars that are as large as the orbit of Jupiter. With such a variety of stars, there are some in particular that strike as very odd and quite a mystery to us. So today we'll be talking about the brown dwarf star. Most of the stars we have today have formed inside huge clouds of dust, mostly composed of hydrogen and helium. These are the two fundamental building blocks of pretty much what makes up a star. Over time, the clouds begin to fall under the influence of gravity and will slowly coalesce together to form what is known as a protostar. This is an early star that is beginning to form, and this is usually the system before nuclear fusion begins. There will reach a point where the cloud is condensed so much that nuclear fusion does eventually begin at the center of the clump of gas. So at this point, a star is born, and the hydrogen fuel begins to burn inside the star core. And this is the basic method of stellar formation. It's the most simplistic version, and almost all the stars in the universe follow the same procedure. However, not all stars make it to the nuclear fusion stage. In fact, there is a specific type of star that is not massive enough to sustain nuclear fusion in its core when it is formed, and so it immediately begins to rapidly cool. So these are known as brown dwarf stars. They are termed as the failed stars, and since they cannot actually undergo nuclear fusion in their core, they cannot be considered as stars in a traditional sense. And so we just drop the name, stars from the actual name. We just call them brown dwarfs. So let's talk about this for a second. Why do brown dwarfs fail at fusing hydrogen in the first place? What factors are there that needs to be considered during the formation process? Why are they failed to begin with? So we've already said that brown dwarfs do not reach the sufficient mass to become a star, as we have learned from, just what I previously said. But there are several other factors we have to consider in this case. One of the more important ones is the temperature factor. And this is important as to why they cannot actually reach the mass that is needed to begin nuclear fusion. So we need to consider the early stages of star formation. So continuing on for what I said earlier about how these are formed, as the mass of all the clouds forming the protostar is going into the system, the temperature at the core begins to increase. In order for nuclear fusion to happen, which properly turns the protostar into a star, it needs to achieve a minimum temperature in order to overcome some of the nuclear forces that are, that are in the atomic scale here. So we basically need a temperature that can allow hydrogen atoms to just merge together to form another type of element. In this case, it would probably be deuterium, which is a hydrogen atom, but it's got two protons instead of the traditional one. Or it could go straight up to helium or other kind of thing like that. So this value changes depending on how massive the star will be. So it's all dependent on the original kind of composition of the gas cloud, how much mass there actually is to begin with. But the lowest this can be is about 10 million degrees Celsius or 10 million Kelvin. At such a hot scale like this, both temperature scale, the degrees Celsius and the Kelvin scales, can pretty much be exactly the same. But, to stick with, how we use things in science, we just stick with the Kelvin scale, so that's what I'll be using throughout the remainder of the video. And of course, Fahrenheit is not used at all, so we're just going to ditch that completely. Sorry to those who use that, but that's how it is. So, this is still unimaginably hot anyway. And for reference, our sun's core is at 15 million Kelvin, so that is still really crazy hot, even if it's the minimum temperature you need. But if the temperature in the core of the protostar system is below the minimum amount when the stars begin to form, then a brown dwarf is formed as a result. This means that hydrogen has failed to fuse together, and so this marks a failed star. It's just a ball of superheated gas that cannot undergo nuclear fusion. I mean, they may be able to do some kind of fusion at the very beginning, but it will just cease really quickly. So that's why we just say it's still a failed star. So you can't really consider it as a star, basically. But, it will then begin to rapidly cool. As a result of that, as there's no fusion taking place, the heat will just keep getting emitted, and so the temperature of the entire ball of gas will just decrease. And so the surface temperatures will drop to, at most, about 2000 Kelvin, which is too cold to be considered as a star. Usual star surface temperatures are way higher than that, at least double that amount. So brown dwarfs cannot be considered as stars because of literally what we just said. So are they just really huge planets then? Because, while they are really cold, they are also not very massive at all. But according to the current definitions, no, they're not planets either. And the reason is because they are far above the typical mass range for a planet's classification. And the upper limit for this is about 13 to 15 Jupiter masses. So that's a mass that is about 13 to 15 times greater than the planet Jupiter. But this value is widely disputed, and there's some ambiguity as to where the line is drawn between what makes a planet and what makes a brown dwarf. So, we just say brown dwarfs are simply a grey area between the boundaries of what we know as a planet and a star. So, how can we detect and see brown dwarfs? If we want to know what these look like, if we want to try and detect them for ourselves, we want to see if they even exist, we need to find some way to find them. So, can we just use usual visible light telescopes to observe them like we can do with other stars? No, not really, actually, we can't. And I'm going to explain why. In the first video of this channel, The Problem with the Night Sky, I briefly defined the concept of luminosity. If you haven't seen it yet, I would recommend to go ahead and watch that. It's an interesting video to explain about all this concept about light and this huge thing about the universe in general. But I talked about luminosity in that, and I've said that luminosity is the power of radiation that is emitted from a star or an object. And so, this just literally means that it's the average amount of energy outputted per second. Now, for those of you who might be familiar with electricity, or may have studied it at school or wherever, or if just simply have probably heard of some concepts of this might be quite familiar to something called electrical power, which is, measured very similarly. It's the average amount of electrical energy outputted per second. The difference is that electrical power is from electricity, and luminosity is occurring from the nuclear fusion inside a star core. So that's kind of the key difference, really. So the luminosity of a star is directly related to its temperature. And so by understanding this, we'll be able to see why brown dwarfs are absolutely, really difficult to detect in the visible range like we can do with the other stars. And why we cannot even find them by just using simple light-ray telescopes. So the relationship for this, for luminosity and temperature is given as the following equation. L is equal to sigma times T to the power of 4. And this is the luminosity-temperature relationship. It is also known as the Stefan-Boltzmann equation law, though this one's a bit more of a simplified model of it. There is an area component, a surface area component, but I didn't include that here. I just wanted to show this relationship, really. So don't worry about that. So to quickly break down this equation, sigma, which is this term here, this is the Stefan-Boltzmann constant, which is a constant value of 5.67 times 10 to the power of minus 8 with units watts per meter squared per Kelvin to the power of 4. And that just stays constant in all cases. That's just a simple value to, we'll see why this is the case, but yeah. T here is just simply the temperature. That's all we really need there. So that should be self-explanatory. And L there is the luminosity. So it's the power output, basically. So what this equation means, and why the sigma is there, is so that we can have what is known as a proportionality. And that is between the fourth power of the temperature and the luminosity. And so what this means is that a small change in the temperature will cause an extremely large change in luminosity. And that can be plotted with this plot here. So we can see that for low temperatures, the change in the luminosity is quite slim, but it's quite shallow. But as you increase the temperature, you get higher and higher. The luminosity values just shoot up, and it gets it gets to the point where a very small change in temperature will account for a really big change in luminosity. So we have said that brown dwarfs normally have surface temperatures of less than 2000 Kelvin, and since they cannot undergo fusion, they'll be continuously cooling over a long period of time, and we've seen that before. We've already talked about this. So from using the plot of the Stefan Boltzmann law, this means that luminosity will also decrease incredibly rapidly over time, even faster than that of temperature. So if we were at 2000 Kelvin, the luminosities would be extremely low compared to other stars out there, and so most brown dwarfs will appear extremely dim or invisible to us, as the other stars easily can just outshine them, and we will pretty much receive almost no light in the visible range, that is. So it seems like, we're kind of out of luck then. We can't really find them with traditional telescopes. But all hope is not lost. Because brown dwarfs keep cooling, and they keep, the luminosities keep decreasing, this happens over an extremely long period of time. And so they are still constantly emitting heat energy as they keep going cold. So we have plenty of time still. We have a lot of time to buy from this. If we can't detect brown dwarfs using light ray telescopes, we can use the next best thing, which is infrared telescopes. And these telescopes quite simply just pick up infrared radiation, which is radiation that is in the form of heat, basically. Radiation that is emitted from heat. And so this is feasible because brown dwarfs are still they're cooling, but they're still emitting heat. And so we can actually pick up that heat using infrared telescopes. So it also appears that brown dwarfs are commonly located inside huge clouds of gases and other regions where visible light gets absorbed really quickly, or really easily. And so even if we could find them, we would not be able to see anything with standard light ray telescopes in most cases, because the light would just get absorbed by the clouds around it. However, infrared radiation, which is radiation from the heat of an object, they can freely travel through these regions without being absorbed. And so this gives infrared telescopes a second advantage, which is that we are able to pinpoint where these brown dwarfs are actually located, as well as, detecting them in the first place. So that's kind of a double advantage right there. Not only we can see how hot they are now, or, can confirm their existence, but we can also see where they are inside huge, dusts, huge clouds of dust and gases and all of that, which would be invisible in the visible light region. So that seems to be quite well off and quite good. So that's what we've been using now to discover brown dwarfs. That is kind of the standard procedure now. So a quick example of a brown dwarf that's been discovered is brown dwarf 2M12071A. So this is a brown dwarf that has one planetary companion, 2M12071b. It is a gas planet that has a mass 4 times greater than Jupiter. So both of the images of both objects are shown here. So this is an infrared image. So this is picking up the heat emitted from the objects. And this is taken with the Hubble Space Telescope, which is shown there in the image. So we're basically just seeing the heat being emitted from the objects. Yeah. So the left image is the brown dwarf itself, and then the right image is the companion planet. And you can see the brown dwarf has been emitted from the right side, just so we can see the planet on its own. And this shows us, this pretty much just confirms, this kind of thing just confirms brown dwarfs do exist, but we need to use different methods to detect them, which is pretty much like this. So with that all said, there are still many more mysteries to be faced with brown dwarfs, and some of the current challenges are to try and mark the boundaries of what defines a planet and what defines a brown dwarf in accordance with, standard, with the current definitions that we use. Hopefully sometime in the future the distinctions will be a lot clearer, but for now we're just going to have to get used to this ambiguity for a while, and as well study a bit more on the brown dwarfs themselves, because these kind of failed stars are not really researched on much, but if we improve more on the infrared technology to be able to detect these, we should be able to get there. Should be able to start looking at composition a bit more, start looking at what regions they really are in, and all that kind of thing, looking at neighbors, and just the list goes on. There's so many different things. So that is for the future, and there's many more things to come. So thank you guys so much for watching this video. If you want to check out my secondary channel, you are free to do that as well. It might not be of interest to most people, but if you want to look over basic concepts of maths and physics and all that, then I would definitely go ahead and check that out. I've recently been uploading on that as of the last 2 weeks, so we can get going. But anyways, that is all for now. I'll see you all in the next one.